Okay, so once a hazard is identified, our goal is to get rid of that hazard in one way or another, or to resolve it. And researchers have come up with this hazard reduction order of precedence, which is the preferred order of attack, if you will, for getting rid of the hazard. It gives the organization generally the most bang for the buck. Starting with priority 1, it's the most effective method of controlling the hazard, or at least at the least expense. But by the time you work down in the order of priority or the order of precedence in the sequence, you're looking at costly methods with a lot less effectiveness really in controlling the hazard. And you may notice that as hazard mitigation strategy gets farther down the line, it becomes more and more dependent upon the human down towards the end, which is generally less effective because it's more prone to error. If safety is dependent upon the design of the system, that can be more reliable generally than the safety being dependent upon the human doing the right thing at the right time all the time. So let's start at the top and work our way down. The most impacting hazard reduction strategy is to design for minimum risk. Design for minimum risk. Eliminate or reduce the hazard. And this requires prior planning, and that's where a lot of times engineers fall short. In the concept design phase of the life cycle, if safety is taken into account before the system is built and in production, it can be much more effective in designing safety into the system. It's much more expensive to go back and redesign safety into the system after it is in production and out on the market. When a product has a safety recall, that is an example of where hazards were later identified in the system and designs needed to be improved, costing the companies generally lots and lots of money. I hope you visited the link in your PowerPoint presentation to the story of the 25 biggest product recalls of all time. The Toyota airbag safety recall tops the list and is also implicated in several throughout the list. That's an example. It cost the company millions to replace the faulty airbag trigger, but more than 8 lives and 100 injuries were also part of that cost. Not so apparent is the cost of $75 million in fines, lost contracts, lost reputations, lost jobs, lawsuits, and so on. Skimping on safety in the beginning generally costs big time in the end. So next down the line, if the system you're designing has hazards that cannot be designed out or cannot be mitigated through the design, we can provide safety devices. That's mechanical devices that shield the operator from getting to the hazard. It blocks the TTO, blocks the operator or the potential victim from getting to the HS, the hazard source. It blocks the IM component of the hazard, the initiating mechanism. It's like a shield on a table saw. The shield on the table saw blocks the operator's fingers generally from getting to the blade. Again, we're expecting that the human does not remove the shield in order to get better access to the blade. So some of these are also still dependent upon the human. If your system does not allow for designing out or down the hazard or providing safety devices, you might provide a warning device. Warning devices let the operator know when the hazard is present. In a house, a smoke detector alerts the occupants to the potential presence of a fire, which is a hazard. From warning devices on down, we're relying on the human pretty extensively. When an alarm or a warning alerts the operator, we require them to do the right thing. The beach jet with a swept wing has an overspeed warning alarm. This is another example. The alarm is obnoxious and it blares when the aircraft goes too fast. It's an overspeed warning. The aircraft's design is fully capable of the higher speed, but the danger is actually with Mach tuck if the aircraft goes too fast and the swept wing stalls. Many flight crews pull the overspeed circuit breaker, not quite understanding the theory of Mach tuck. Many flight crews pull the overspeed circuit breaker so the alarm will not disturb the passengers in the back. And that's an example of humans overriding safety and warning devices, which again is very dangerous. Just like removing the shield on a table saw. If none of the above works, then special procedures may be employed to mitigate the hazard. This is by far the least effective because it requires the human to do the right thing at the right time all the time. Special procedures are like checklists, maintenance procedures, operational procedures, etc. And they're effective, but they're not as effective as the higher in the order of precedence. Working down through the hazard mitigation precedence should give the engineer ample opportunity to think outside the box and try to work out ways to mitigate the hazard. Keep in mind that if it cannot get to an acceptable level, the risk may not be worth the reward. Always keep that in mind as well. But try to think outside the box before we get to this point, because the system may be very valuable. We just need to figure out how to design out the hazards. Mitigating the hazard is one thing, but we can only mitigate what we know is there. Identifying the hazard, like we said before, is sometimes the most difficult part of system safety. In the next video, we will discuss hazard analysis types, which are systematic ways to identify hazards throughout the system.